It's my pleasure to introduce Jessica Fintzen from University of Cambridge and also Duke University, who will speak about representations of p-adic groups and applications. And I remind you, if you have questions, please wait until the end if possible. If it's urgent, please raise your hand or contact me. So Jessica, please go ahead.
Thanks. Thank you very much for the invitation to speak here. First of all, I'd like to encourage everyone to turn on their video. It's like in a regular talk, not that 90% of the people bring a blanket to hide below. Great. In particular, grad students and postdocs, I encourage you to turn on the video. Now that there are many videos, I'm not able to see everyone. So if you wave and I don't see you, please don't blame me. While we are encouraged not to interrupt with questions, you're welcome to write a question in the chat. I just opened the chat and I try to keep an eye on it. But please, I mean, again, I might not be able to see it, but you can give it a try. All right, okay. So I want to talk about representations of p-adic groups and their applications today. So this talk is not aimed at people who work in representation theory, but more aimed at people who might want to use results from representation theory, who might want to apply them. So I might not dive into the details of the groups, but more give you an idea of what's out there and give you an idea of what are questions with which I could help you. So I've been recently asked several times, like over the course of the summer, several people asked me, what is the state of the art? What do we know about the representations of p-adic groups? And so the first half of this talk will be an answer to that question. And afterwards, I like to show you an application and give you some ideas of what are the kind of questions I could help you with. So mainly there are two things, like if you want to deduce properties of a representation from compact open subgroups, I might be able to help you. Or if you are able to prove something for GLN using representation theory, in particular using explicit representations, but don't know how to do it in general, maybe I might be able to help you. So don't be afraid of approaching me. All right, so that's the idea of today. Oh, sorry, before I start, let me share my slides in the chat. So I don't think you need them. I hope you just listen to my talk, and the slides are created in a way that I hope you can follow. But just in case, the slides are now in the chat. Let me see. Okay, participants should be able to share this one. All right, so let's start. So what is the setup? So I want to work with capital F, which is a non-Archimedean local field, so it's a finite extension of QP, or the Laurent series over a finite field. Inside there is F, which contains O and the ring of integer, and a maximal ideal P. And the residue field is FQ. And so the main player for today is denoted by G, which is the connected reductive group over our local field F. So for example, GLN, SLN, SON, SP2N, but also exceptional groups and all kinds of crazy ideas you can come up with. All right, so what is the motivation? What's the long-term goal? The idea is that we want to construct all representations of this group G, this topological group G. And we want to focus on the building blocks, we want to focus on the irreducible one. And in order to have a reasonable category to study, we study the smooth representations. So those that satisfy the property that for every vector in the vector space, the stabilizer contains a compact open set. And I want to study representations that have complex coefficients, or alternatively also mod L coefficients, FL bar coefficients, where L is a prime number different from P. And I denote the results from mod L coefficients in blue. So before I tell you what's known, I want to just outline a few applications. So first of all, if we know how to construct representations, that will help us for the representation theory of p-adic groups itself. So for example, if we want to study the theta or Howell correspondence, or if we want to calculate the Harris-Chandra character of a representation, or if we want to study distinction, which means we want to restrict the representation to subgroup and then see if it contains the trivial representation or not. For all those cases, it's important to know how the representation actually looks like. So most results that we know up to today rely on knowing explicitly how to write down representation. Another application is towards an explicit local Langlands correspondence. So if you want to try to write down a Langlands correspondence, if you want to associate to every representation of a p-adic group, a representation of a Galois group, an L parameter, in order to do this explicitly, you want to know how these representations actually look like. Another application is towards automorphic forms. That's an application that I would like to talk about at the end of this talk to give you an example of an application. So that's a joint work with Serre. And there are also other applications. I've seen it in p-adic automorphic forms or used in the p-adic Langlands program and various other places. And I put a ... here because I hope that the ... is something that we can fill in together. So if you have any idea for application, please don't hesitate to reach out to me and we can try to work on it. All right, so that's a sample of applications. And now I want to move on to actually tell you what we know about representations of p-adic groups. So as I said, we want to construct all of them ideally, and we want to focus on building blocks. And the building blocks, these are the irreducible supercuspidal representations, or in the model setting, they are called cuspidal representations. For those who don't like the word supercuspidal, I always tell people not to be scared. It just means building block. Mathematically more correct, it means that it's not a, let me formulate it differently, mathematically correct, every representation occurs inside the parabolic induction from a parabolic subgroup to the whole group of a supercuspidal representation. And the supercuspidal representations are those that only occur in the parabolic induction from the group to itself, so not in an actual parabolic induction from an actual subgroup. So that means we can write down these supercuspidal representations. In some sense, more or less, we can write down everything. And it's easy to write down parabolic induction, but it's not easy to write down supercuspidal representations. So people have struggled for a long time to write actually down a supercuspidal representation. And so what do we know in general now? So it started with the work of Howe and Moy, who studied GLN like 50 years ago. And that was basically the first group people looked at. I think that's a common theme. And then the story was finished by Bushnell and Kutzko, and now more than 25, almost 30 years ago. And they gave a construction of all the supercuspidal representations. And my friend Shimura showed shortly afterwards that actually the same construction also gives all mod L representations. So now we can write down all the mod L cuspidal representations as well. And if you go beyond GLN, the next case that people often look at are classical groups, so that are fixed points of involutions inside GLN. And if the prime P is not equal to 2, then Stevens showed in 2008 that all represent how to obtain all the representations. So he gave a construction of all the supercuspidal representations. And recently, Korenchuk and Stevens showed that a similar construction also works model. And Serre and Stevens treated around 2008 also inner forms of GLN. And these are all following roughly the same idea. So the classical groups and the inner forms, they still use basically the setup of Bushnell and Kutzko, but just make sure that things are invariant under the involution or behave well when you go to inner forms. It's non-trivial, but it uses some of the same language. And what I'm interested in is now to go beyond this case, go beyond classical groups, beyond GLN. So what I want to talk about today is what can we do in general? We take a general reductive group. This includes GLN, but can also include groups like G2 and other exceptional groups. And so there, we know much less. It took much longer to write down supercuspidal representations. And it started basically in 1994, 96 with work of Moy and Prasad. And they introduced the notion of depth. So the depth of representation can be 0, or it can be a positive real number. And I'm drawing the depth here and downwards. And so the depth is an invariant that they associate to a representation. And then I want to draw the picture in this direction of the picture. I want to draw the prime number, because some results depend on the prime number P, so the residue field characteristic. Oh, let me actually just spotlight myself now, just to be safe. So it depends on the prime number, some of the results. That's why I draw the prime number in that direction. And what Moy and Prasad did is they studied the depth 0 representations, so all the representations here at depth 0, and showed that they correspond to representations of finite groups of Lie. And Morris did the same in 93, 99, using somehow a different approach using p-adic. So that means for the depth zero case, we more or less know everything. We know it up to knowing how representation of finite groups of Lie type look like, which is very complicated. But we are interested to go deeper down and look at higher depth representations. And so in 1998, Jeff Adler constructed some representations of higher depths. So these are the blue dots here. These are representations of higher depth. And 3 years later, JKU generalized Adler's construction vastly to provide all these dots that you can see here. And I should say JKU's representations are the representations that everyone works with nowadays, or almost everyone works with nowadays. So when I say that these representations are used, or these constructions are used to study the theta correspondence, calculate Harris-Chandra characters, study distinction, write down local Langlands correspondence, all these results for general reductive groups use JKU's construction. So JKU's construction is really the heart of what we can do. And since JKU's construction is so important, it would be helpful if this construction gives us all representations and not just some examples. And so this is indeed true, at least under some assumptions. So in 2007, Julie Kim proved that actually, if we are in this region here where the prime is very, very large, and if we assume that the characteristic of the field is 0, so if we work with a finite extension of QP, then we get all representations from JKU's construction. So we get exhaustion in this region. So this means that all the results that we have proven so far for JKU's representation now hold in full generality for all representations, at least under the assumption P is very large and the characteristic of F is 0. And so now you might wonder, is this everything? Can we prove that we have exhaustion everywhere? And so Reader and Yu in 2014, they provided a new construction of representations, and they called the representations Epilogical. And so here are some representations that they constructed. And the construction is very nice because it's much easier, in some sense easier, than Yu's construction. But the representation they obtain are representations that are very close to the surface. And that's why they call them epilogical representations. Because the reason is that Mark Reader thinks of a representation as a fish in the ocean. So he thinks that all these dots are fish in the ocean that we try to understand. And so he constructs, or together with JKU, they construct representations of smallest positive depths, so close to the surface. And so in oceanography, the upper zone of the ocean is called the epipelagic zone. And since they construct representations in that zone, they call them epipelagic representations. So that's what they constructed here. So the nice thing about the construction by Reader and Yu is that they take a rather simple input, something which they call a stable vector in the multi-substitution. And what I've shown in the special case, it's joint work with Beth Romano, is that actually this input for the construction by Reader and Yu, this exists for all primes P, also for small primes. And this actually provided new representations here in this area where the prime P is small. So it turns out that not all the representations arise from JKU's representation. There are more representations. And some examples are provided by the epipelagic representations that come from Reader and Yu's construction using the input that Beth Romano and I, or in this general case that I proved exists. So that means there's more out there. So what is the next thing to do? So the next question is, how can we construct all the representations? So what else is there? And that's my future work in progress. Unfortunately, it's not, I have work on sketch paper, but I don't have enough to be able to talk about it today. So that's something for some other day. What I want to talk about today is, what do we actually know? And so if you see this region, here's the region where the prime P is large, not just very large. And there are a lot of dots here. So the question is, in which region do we get everything from Yu's construction? So in which region do all the results that we have for Yu's construction hold true? And it turns out that we get exhaustion in the region where P is large, not very large. I'll make precise in a second what this means. And moreover, you see that there's this restriction on the characteristic, which is also not particularly nice. So I also removed this restriction. So let me make this statement precise. The theorem is that suppose the group G splits over a tame extension. This assumption is there because use construction only works for tamely ramified groups, for groups that split over a tame extension. And then assume that P doesn't divide the order of the Y group. So what does it mean that P doesn't divide the order of the Y group? So for GLN, the order of the Y group is n factorial, so it means that P is greater than n. For classical groups, we exclude basically all the primes up to n. And for exceptional groups, we exclude in worst case 2, 3, 5, and 7. So we don't actually exclude that much. And while P very large, we really exclude a lot. So it depends on the field F and might become arbitrary much. And so the statement is that if P doesn't divide the order of the Y group, then use construction indeed yields all supercustom representations. So we have exhaustion in this whole region. And moreover, an analogous construction also works in the mod L world. So we can also work mod L, not just in characteristic theory, under the same assumption. So that's basically the state of the art. So I could stop here. Unfortunately, oh, sorry, maybe I should say something. Why do I think that this is the best thing we can do? I also showed that actually P doesn't divide the order of the Y group is optimal in general. With a small, I mean, I put a small star here. You can look at the paper that I put on the archive in January 2018 for the details. But the idea is that if you not only look at supercustom representations, but more general types, and look at all inner forms at the same time, basically what I show is that the input for use construction exists if and only if P doesn't divide the order of the Y group. So there is a serious obstruction to this smaller part here. So it's not just that we weren't good enough and we just couldn't prove that use construction is exhaustive. It's not exhaustive. We have seen examples before. We have seen there are more representations, but also expect it's bound to be optimal. All right. So unfortunately, there's another small problem, which is that it was encountered that JKU gave a construction of representations, and then he proved that his construction actually gives us supercustom representations. But unfortunately, his proof doesn't work. More precisely, there's a typo in one of the references that he quotes. So what does he do? He says that, or he cites a result, which is a result from a long time ago, where I think people wrote papers still by hand and gave it to a secretary who then typed it for them. And in the final version, there's a ±1 missing. So there's a statement, and the ±1 is missing. And if you use the statement without the ±1 the way it's printed, then JKU's proof works. But unfortunately, the ±1 has to be there. If you read the proof of the paper, it has to be there. And if you put the ±1 in, the proof breaks down. It just doesn't work anymore. So more precisely, I showed there exists even a counterexample to the key ingredient in use proof, which are this proposition 14.1 and theorem 14.2, if you are curious and want to look it up. But it's just some technical statement. It's a statement about the space of some intertwiners. And if you put in the ±1, it just falls. So that means the whole proof breaks down. Of course, I guess I wouldn't talk about it if I couldn't fix it. So luckily, use construction still yields all supercustom representations. So what I did is I provided an alternative proof that doesn't rely on this false statement in the literature. So that means all the results that we have proven about JKU's construction, all these results still hold true. All right, let me see, are there any questions at that point? Okay, I don't see any questions in the chat. Either my chat is stuck or there are no questions. So then this is actually now the situation we're in. And I want to say a bit more about how these supercustom representations look like to give you an idea what they are. So there's a folklore conjecture that all supercustom representations or constructions arise in the following way. There's a two-step process. The first step is you construct a representation rho K of a compact mod center open subgroup K inside your group G, for example, of SLN over ZP inside SLN over QP. And then the second step is that you build a representation of the full group from this representation. And the second step is just compact induction. And so I want to give you an example so that if you leave this room, okay, leave your own room at the end of the day, that you have seen a supercustom representation. So I want to give you the example where G is equal to SH2. And I need a compact open subgroup, because I said we start with a compact open subgroup. So I take this compact open subgroup. So these are matrices in SH2. So these have determinant 1. And I take the center as well for some technical reasons. And then I take a representation. I need a representation. And I want to construct a one-dimensional representation, so a character. And the way I do it is plus minus 1, I just send to 1. Or you can send it to plus minus 1, whichever you like. And now I have to tell you where to send this matrix. So what is this matrix? This matrix is actually a piece of the Moy-Passat filtration. So let me see if my pen works. It works. So let me just say a few words about what is this? What's the Moy-Passat filtration? So first of all, what is this X here? So this X is the point in the building. Okay, what is the building? The varieties building is a lot of real spaces glued together. So in the case of SH2, it's a lot of lines glued together. So a lot of infinite lines glued together. No, I'm not that great at drawing. And so if we work with the field of 2, for example, this infinite tree has valency 3. And so you see here, so for example, this is a line, this is an infinite line. And there are a lot of one-dimensional spaces. And now this point X is the point in the building. So this is our X. And so the Moy-Passat filtration is now a filtration that Moy and Passat attach to this point. So the zeros filtration subgroup, GX0, in this case, this is just it's O on the diagonal, P in the upper right corner, and O on the lower diagonal. So this is roughly just the stabilizer of this point X. So the group itself acts on the building, and this zeros filtration subgroup here is just the stabilizer of that point. And I said now we have a filtration by compact open subgroups. So I said in this case we have the 1/2 filtration piece. So how do I get the filtration? So the zeros piece is just fixing this point. And roughly speaking, it's not quite precise, but roughly speaking, the way you get a filtration is by fixing balls of larger and larger radius around this point. So if you do that, you obtain a filtration subgroup of depth 1/2, which is obtained by 1 plus the maximal ideal on the diagonal, while the off-diagonal terms stay the same as before. And you have also groups in between. All the groups in between are the same. So this is the same as GX1/4 or anything in between. And the next interesting group would be GX1 filtration subgroup of depth 1, where what happens is you keep the diagonal to be 1 plus P, and the off-diagonal terms change. They become slightly smaller. So you get a filtration by compact open subgroups, which is very important in the construction of supercustom representations. Don't worry about the details. I just wanted to tell you there's this underlying filtration that can be important. And basically to think of it is you act with the group on the building and you fix larger and larger and larger balls. That's basically what it is. And so now we start with this filtration subgroup of depth 1/2 here. And we want to construct a representation of that group, of that compact open subgroup. And so the natural thing to do is to mod out by the next filtration subgroup. And so that's what we do. So we will mod out by this next filtration subgroup. So that's what I do on the next slide. I mod out by the next one. I call it 0.5 plus the next one. And what is this quotient? So this quotient, the only thing that changes are the off-diagonal terms. So the quotient just has the residue field on the off-diagonal. And what do I do with an element there? I can just map a matrix AB to the sum A plus B. And that's an element of the finite field, and I can just map the finite field to the complex numbers. And then I can just look at this composition here. This gives me a map from this compact open subgroup, to the complex numbers. So it gives me a character. So that means this way I constructed now a character of a compact open subgroup. And now I can build a supercustom representations via compact induction. So that just means like regular induction with all the functions. transform under this representation, under this character on the right. And compact induction just means I want the functions to be compactly supported. And then the action is just via translation. So that's an example of how supercustom representations look like. And general supercustom representations arise in the same way as compact induction. Just this row K and this K, they get much more complicated. So JKU's construction doesn't work just with one of these filtration pieces, but it works with a lot of filtration pieces of a lot of subgroups. So you take a bunch of twisted Levy subgroups, and for each twisted Levy subgroup, you take a filtration piece, you glue all these filtration pieces together to get your big compact open subgroup. And then in each of these filtration pieces, you have a character, and then you glue all these characters together. And then you enlarge it slightly in order for supercustom fidelity to work in the end, and that's what you do. So it's the same idea, but just much more complicated. But this is an example, so now you've seen a supercustom representation. All right, so after seeing one, I want to tell you a slight addition to it. So I said that I proved that use construction still works, and that this compact induction from some compact open subgroup to the whole group of some representation gives us these supercustom representations. But still, use proposition 14.1 and 14.2 are wrong. So the advantage of my proof is that it makes it much shorter because proposition 14.1 and 2 were complicated. So my proof basically uses half of JKU's proof. It's not independent. But then instead of the second 20 pages, I just add a 3-page argument in. But on the other hand, this 14.2 and 14.3, these are results about dimensions of intertwined linked spaces. And these are really important for applications. So for example, if you want to study hacker algebras or calculate character formulas, they might become important. And so that's why we might be interested in actually fixing this. And that's joint work with Tasha Kaleta and Lawrence Spice. So what we did is actually we proved that there existed quadratic characters, a map from this compact open subgroup to ±1. Remember that the problem with use construction was there was a quadratic character in a way that wasn't supposed to be there. So our idea is to basically twist it away. So we say there exists a quadratic character such that if we twist the representation row with this quadratic character, then JKU's proposition 14.1 and theorem 14.2 hold again. So that means that provides another fix of JKU's construction. This time it's much longer because you have 40 pages of JKU's construction and then the 25 pages of showing that this character exists. So even though it's just a quadratic character, it's non-trivial to actually construct it. But the advantages of the second approach is that there are a bunch of applications, and that's actually the motivation for why we did it. So first of all, where's this character coming from? This character, epsilon, somehow was lurking around already. So Lawrence Spice, for example, he tried to calculate Harris-Chandra characters, character formulas for these supercustom representations. And he recently had a compositio paper in which he proved how to calculate them basically, but it relied on this character to exist. So he had a conjecture in there that needed to be true for everything to work. And even earlier, we have seen a certain character pop up several times when people try to prove local Langlands correspondences in special cases or try to calculate these character formulas. So one application is that the abstraction for Lawrence Spice's work is now going away. So hopefully you will be able to calculate now the character formulas. Second application is that, so on the one hand, there was Lawrence character, which alone didn't quite lift, his character was defined on a torus, but we needed on all of K to do something, and it didn't quite work. But then Tasha Kaleta tried to write down a Langlands correspondence for so-called non-singular representations, which corresponds to all the supercustom parameters. And when he did this, he encountered another sign character, another ±1 that was an abstraction. And so he conjectured that his character, which was also defined only on the torus, could be defined on all of K, so the construction vanishes. But again, Tasha Kaleta's character didn't really do that. We couldn't lift it. But it turned out that if we take the product of Lawrence's character and Tasha's character and add in some auxiliary ones, then we actually obtain the epsilon here, which does the job for both. So that means one application is we get character formulas. The second application is that we are able to write down a local Langlands correspondence candidate for it in the non-singular representation. And another application will be hopefully that once the character formulas are available, then we can actually prove the character identities for the local Langlands correspondence, of course, so-called regular supercustom representations that was written down earlier by Tasha Khalifa. So that's work in progress. So it seems like this one, it's just the character. It seems to, this just ±1 seems to have a big effect. And basically, I think the way one might see it is maybe that use construction was not the canonical one, but the canonical construction is the one that's twisted by this character epsilon, because then suddenly all these identities work out and all these characters formulas look very nice and look much more natural. And hopefully there will be also applications to hacker algebra identity. All right, so that's the end of the part that I wanted to tell you about the construction of supercustom representations. What I want to do next is to show you an application. I want to talk about the joint work with Serre. And for this, I should talk a bit about types. So, what is the theory of types? The theory of types is a generalization of the theory of supercustom representations. And the idea is that the theory of types allow us to obtain information about the representation of G by studying representations of compact open subgroups. I'm asked if when I write character identities for the local Langlands correspondence, I mean endoscopic character identities, specifically stability of proposed L packets. Yes, correct. That's precisely what I mean. So the endoscopic character identity and the stability, that's what we try to prove. Further questions on that point? All right. So I was talking about the theory of types. The idea is to obtain properties of the representation from properties of a compact open subgroup. So for example, with supercustom representations, the group is semi-simple. I claim that, we conjecture they are induced from compact open subgroups. So in other words, it means that if you have an arbitrary representation and restrict it to this compact open subgroup that gives you the supercustom representation, and if it then contains this row K that you've seen before, then it means it's actually the supercustom representation. So for supercustom representations, all the information is contained in this compact open subgroup K and a representation of it. And in general, the idea of types is usually to pin down Bernstein blocks for those who know what Bernstein blocks are. And these types usually consist of large compact open subgroups together with an irreducible representation, which is often complicated. But there are other applications you might be interested in. And one of those applications is supercuspidal type. So what is a supercuspidal type? A pair K row consisting of a compact open subgroup and a finite dimensional representation row is called a supercuspidal type if the following holds. If for every irreducible representation pi, if the representation pi restricted to K contains row, which means that this Hom space is non-zero, non-trivial, and contains more than 0, then this representation pi is supercuspidal. In other words, the representation row of the compact open subgroup K detects supercuspidality. Why might you be interested in it? For example, because if you study automorphic forms that have a supercuspidal component are often much easier to deal with. So that's one of the applications that we are going to see. So let me give you an example. So we've seen SH2 of F before, we've seen its compact open subgroup, and then if you take the representation row K from before, this gives you a supercuspidal type. What are the representations that contain row when restricted to K? It's the representation you've seen before, and it's the representation that you obtain similarly to before, but sending this ±1 to ±1 instead of just 1. You might remember that I said that you need to send the center somewhere and it doesn't matter, but there are 2 representations, but they are both supercuspidal. So that's an example of a supercuspidal. And so what we are interested in, and what I'm interested in the joint work with Serre is what we call omni-supercuspidal types. So this is another step forward, which is, maybe before I go into the details, let me say, so types for Bernstein blocks usually, as I said, consist of compact open subgroups together with a representation that's usually not a character. But for applications, it's often interesting or often important to have a character, because a character is much easier to work with. So that's why we, in our joint work, we want to look at types that actually consist only of characters. So that's why we don't care about just the Bernstein blocks. We don't just care about pinning down one supercustom representation, but we are happy to pin down like 50 different supercustom representations, as long as they are all supercustom. So we're giving up some precision on what representation we pin down. But at the other hand, this allows us to work with a character instead of a higher dimensional representation bouquet. And so we say that an omni-supercuspidal type of level p to the m is a pair that consists of compact open subgroup U and a character lambda. So what is lambda? Lambda is not just a character, but in our setting, lambda is a map from this compact open subgroup to Z mod p to the m. So it's a surjection. But then before I said, okay, we want a character, so we want something with values in C star. So what is this lambda? So the property of this pair should be that if I compose this lambda with the map from Z mod PM to C star, which I don't care what map it is, as long as it's non-trivial. So it could be a map that sends almost everything to 0, as long as it's non-trivial. So it usually just sends Z mod P to the M to the P smooth of unity in some way. If you compose lambda with psi, so if you look at this character that you obtain, then I want U, this character to be a supercuspidal type. In other words, I want that if you take a representation, restrict it to U, and it contains this psi composed with lambda for any psi that's non-trivial, I want this to pick out a supercuspidal representation. This might look a bit complicated, but the reason we do is simply because of the application that you will see. That comes from, if you want to prove congruences between automorphic forms, that's precisely what you need. So this is what we are interested in. But in general, I think the thing you should take away is what we want is compact open subgroups with something easy, like a character to pick out supercuspidality. And the idea is that we want to use this to pick out from all the automorphic forms those that have a supercuspidal component at some point. And so that's the definition. But in order to use this definition, we need to show that actually these things exist. And so that's the result. So that's the big result about the representation theory that I afterwards show you then has applications outside representation theory. So the result is the following. You can find a draft on our webpage. I assume that the group G splits over a tame extension. The reason we do this is because we work with Hughes construction, which assumes that the group splits over tame extension. Assume that the character of F is equal to 0. Assume that the characteristic of the field F is equal to 0, and assume that P is greater than the Coxeter number. The Coxeter number, this is just slightly greater than assuming that P doesn't divide the order of the Y group. It's just because it makes our life easier. I hope the statement works for all primes P, but in order to prove it for all primes P, we first need to prove more representation theory results. We need to construct representations beyond use representation. So that's why we didn't put much effort into finding the optimal P, because I expect this result should hold more generally. Then under these assumptions, there exists a lot of omni-supercuspidal types. More precisely, there exist omni-supercuspidal types, U m lambda m of level p to the m for every integer m. And moreover, they have the property that we have a decreasing sequence of subgroups. So U1 contains U2, they are all normal subgroups containing each other. And this collection of compact open subgroups forms the basis of neighborhoods. And why is this important? This is important because in the application, this allows us to obtain automorphic forms of arbitrary small level. And this is actually the difficult part here, because usually if you work with types for Bernstein blocks, these compact open subgroups never tend to 0 or tend to 1. They are always rather large. So that's a big difference. All right, so that's the local result. Don't worry if this looks technical. I just wanted to show you how some of these results can look like, in case you maybe recognize something and think, oh, you could do something with it if you knew something about compact open subgroups. And so why is this now interesting? So this is interesting because there are various applications. So one application is that we can obtain congruences between arbitrary algebraic automorphic forms and these that are supercustom at P, at least for groups that are compact, not the center at infinity. I will make this more precise towards the end of the talk afterwards, if people are interested in it. Another application that Pascunas kindly pointed out to us is that also with these results, we obtain that the classical automorphic forms with fixed weights that are supercustom at a prime P are dense in the spectrum of the Hacker algebra. So that's based on work by Emerton and Pascunas. And that's another example. So Emerton and Pascunas, they were done general theory based on capture, and then they applied it to the special case of unitary groups where the group of interest, the local group, is GLN. And so now, thanks to our result works for general G. We can obtain the same result. We can just input our local result and obtain the same result for general groups. So that's what I mean with I encourage you, if you have results for GLN that rely on knowing how representations of GLN look like, maybe I'm able to help you to generalize this result. All right, so these are some of the applications. Why are these applications themselves interesting? So these applications, for example, can be used to assume that an automorphic form is supercustom at a prime P. Okay, that's just a very rough statement. So what do I mean by that? So for example, if you look at the global Langlands correspondence for GLN, the way it started is with work of Clausel in 1991, where he said, okay, let's take a nice automorphic representation of GLN, such that this automorphic representation is essentially square integrable at some point. And then Clausel constructed some p-adic Galois representation associated. And now you see that that we have this assumption here about the essentially square integrable. And so being essentially square integrable is something that's implied by being supercustom. So knowing that something is supercustom at a prime is enough to obtain this result. And so this result only worked with knowing that one component is supercustom. But now one of the applications of our result is that we can remove this assumption about square integrability. So we can remove this assumption here. So basically I could cross it out. So that's the application here. I mean, I should say that this is not a new result. So this was obtained by work of a lot of people before. I mean, I should mention a lot of names. So after Clausel, there was Harris and Taylor. They made this correspondence more precise, also in unramified places. And then Shin and Clausel, Harris, Labette, and Genevieve and Harris, they removed this assumption here. So this is nothing new. But on the other hand, the way they removed these assumptions used a lot of difficult techniques. It used eigenvarieties, elaborate geometric and endoscopic arguments. And what we do now is we just have this local input and it just basically comes out of it. So it's just a consequence. All right, so I mentioned here, so in our joint paper, the joint paper with Dr. Shin, we show that's an application of part 1. Pascunas wrote an appendix for us in which he showed that actually this result 2, which he proved already, was that Emerton also implies the same. And he doesn't have an assumption on the prime because he works with Bushnell-Kutzke types and not with the JKU construction. So ours is still under the assumption that P is sufficient amount. While this is just reproving an existing result, we hope that these applications 1 and 2, and like these techniques of removing these conditions, might be helpful to also construct the global Langlands correspondence beyond GLN or unitary groups. But that's all dream. We have to see what happens in the future. But if you're ever in the situation that you say, oh, it would be helpful if my automorphic form was supercustom, maybe we might be able to help you with that. All right. So in the remaining, I think, 5 minutes, let me just make more precise what I mean with the first result here, the congruences between arbitrary algebraic automorphic forms and those that are supercustom. So for that, I need to introduce the global set. Or are there any questions at that point? Let me see. Okay, nothing in the chat so far. So for this, we work with a global group. So for simplicity, let curly G be a connected reductive group over Q, such that it's compact at infinity, or just compact mod center. Then I want to take the adults to, over Q to be A. I fix a compact open subgroup away from P, so that I was asked if the hypothesis that characteristic F is 0 is necessary in theorem 6. So theorem 6 was this result here, and indeed it is necessary to be equal to 0 because we work with level P to the M. So basically what we need is that P to the M minus 1 is non-zero, which if the characteristic is P, then this is not satisfied. On the other hand, the main ingredient to prove theorem 6 is still valid in other characteristics. It's just this final conclusion where we work level P to the M that really needs this assumption. So that's why we work with the characteristic 0, with F being of characteristic 0. That's why I work with Q in a number field and not with the global function field. So then we also fix the compact open subgroup at P, and then the automorphic forms that we work with. On the one hand, the algebraic automorphic forms. So these are just functions on the double coset. Yesterday, this was denoted by S. I like to denote it by M. So this is just a finite set. So this is just very easy space. So this is one set. So these are the arbitrary algebraic automorphic forms. And then the second set that we are interested in is the following. So in order to introduce it, I fix an integer m, and I denote by am this ring of power series mod out by 1 plus t up to t to the p minus m minus 1. So this is, so this here is basically just 1 minus t to the, oh, sorry, you can't see this, 1 minus t to the p to the m divided by 1 minus t. This just means we add the p to the m's roots of unity to it. And then we also have an action of this subgroup of GQP on this space, on this ring here. And then we can define the automorphic forms with coefficient in this ring, where now UP acts via this action. So UP drops out via this action on AM instead of acting constant. So why are we choosing this ring? So this is actually, this was already in a paper by Schulze, who treated the special case of where the local component looks like GA2. The reason is that if you look at AM and mod out 1 minus t, so this means that in this, that means in this sum here, you set t to be equal to 1. So this sum here just becomes p to the m. So this means you just mod out p to the m. So this is actually the same as isomorphic to ZP mod p to the m. And this is the congruence that I'm referring to. So now the result is that under the assumption that p is greater than the Coxeter number, there exist these compact open subgroups, one for each m at p. So these are compact open subgroups of GQP, such that we have a congruence of automorphic forms, where on the left-hand side, we have arbitrary automorphic forms. On the right-hand side, we have automorphic forms with AM. And so I said we want to have automorphic forms that are supercustom. So the other condition is that this space consists only of supercustom automorphic forms. More precisely, if a representation pi contributes to the space, so if we handle the space with QP bar, so if we get a space of automorphic forms, then we want that if a representation contributes to it, we want that its p component is supercustom. So that means these two conditions together means that an arbitrary automorphic form is congruent to an automorphic form that is supercustom at a prime. It's not really congruent on the nose, it's this congruence using AM, but this is the congruence we need for applications. And in order to actually take all arbitrary automorphic forms, we also require that these compact open subgroups become smaller and smaller and smaller. They form a basis of open neighborhoods. That's why I wanted these UNs to become smaller and smaller and smaller, so that we really get all the automorphic forms. And the last technical bit is that actually what's really important is we have the same identity for the Hecker algebras that act on each of the spaces, and that's what you actually use in applications, the Hecker algebra isomorphism. Okay, I think it's time to stop. Thank you.
Thank you very much, Jessica. Let's show our appreciation to her. And are there any questions? Feel free to raise your hands.
I guess I answered the question already during the talk. I'm also happy to take more questions once the recording ended if you don't like to ask questions on video.
Yes, we can do that too. Okay, maybe we stop the video for now and thank Jessica one more time.
Thanks.